Okay, hello. So let's do a technical deep dive into impact. And I'm going to do it in two different sections. The first section is more abstract, like how does impact work? And then we're going to actually read through all the code of impact in the second part. So impact is a state management tool. And typically when you use state management tools in React, you go and you choose something global. And impact also has a concept of a global store. But where its like power comes is that you can mount stores related to the component tree. So you might have an application that has a global store that you can use in a component, but then related to a specific page, or maybe you need to resolve a session or whatever, you provide a store in the component tree. And this store might receive like a user, for example, that's been authenticated. So you can give that store some props, and that store lives in the observable context, which means that it's not part of the reconciliation loop. It lives in its own observable context, but it can still use other stores. So the store we see here can also use the global store. And then any nested component is able to consume state management from this store. And then you might mount like a specific page or maybe a specific feature, and you want to provide another store to manage that state. And again, we mount a store provider, we can pass some props into the store, and again, you have this observable context where you can define your state management. And again, the store is able to use other stores higher up in the React context, all the way up to the global store. And any nested components is able to use the store. So it's the context mental model that you know, only that the context has an implementation of an observable store instead. That's not part of the reconciliation loop. So the way I can think about this is like you kind of have this React world with components where you have the React reconciler and you build your UIs there. And then you have these stores, which is part of the impact world, and it's like an observation context. And when React reconciles and you provide the store, you're able to pass values into the store that you're providing as props. But on their way into the store, they become signals because now they're represented in an observable world, which means that whenever React reconciles and those props update, it will actually trigger the signal inside the store. And when you consume a store, you consume the signals of the store, but they're represented in the component as if it were just plain values. So it's a very like straight line between the React world and the impact world, where they have a way to look at values in different ways, but it's tied together. Now, what actually happens under the hood here is that when you do provide a store, you actually use something called a store container. And we'll see that in the code later. And that store container is responsible for resolving stores, because it's not only the store that's tied to the store provider, that store might use other stores. And that's the responsibility of the store container. It's kind of like an injection type of container that resolves the stores that this store depends on. So when a component uses a store, it goes up and finds the context to the nearest store container and resolves the store there. And then the store container is responsible to ensure that the store is actually instantiated, and the stores that this store depends on is also resolved and instantiated. Now, a tricky thing about state management is that when you, and especially when we instantiate these stores as we are in the rendering phase of React. So when you render out the component tree, you want to provide a store, you want to render some nested components that should be able to directly consume state during the rendering phase. And that means that we can't wait for component did mount or component did mount or like a use effect to instantiate the store. It needs to happen during the rendering phase. And the reason this is a problem is because of concurrent mode, because React is able to run the rendering phase where it will initialize the store, but then it might suspend that rendering because some nested component uses a promise which throws to the suspense boundary. So that component tree is stuck in the rendering phase until that promise resolves, and it changes into the commit phase where we actually get the component did mount. And also later the related component will unmount when that tree unmounts. So what can happen here if we didn't handle it is that you render out the component tree, you render out the store provider, it initializes the store because a nested component tries to use it. It uses a promise from the store and throws to this suspense boundary that's higher up in the component tree than the store provider itself. So the store provider itself is like stuck in this rendering phase. Now, if the promise resolves and the component tree is committed, everything's fine. But if the promise doesn't resolve, you just navigate, you make an interaction in the app, and this rendered component tree that's not been committed yet is just thrown away because of concurrent React. There's no hook in React that tells us that this happens. Like as a library author, we never know when this happens. So that basically means that store providers, they don't support suspense. And this is handled inside the store provider, so you don't like accidentally stumble into this. But you'll also notice in practice that you don't really get into this issue. But we do have protection in place for this. But it's an interesting thing. Like we talk about concurrent mode, we talk about suspense, but what is this render phase? What's the commit phase? What are the scenarios where React kind of goes into this concurrent mode where it just throws away component trees and so on? I personally haven't found like much documentation on it. So, but this is a very concrete example of how it works. Okay, so I thought we could just basically go through all the code of Impact. It's about 800 lines of code, a little bit more with typing, and it's heavily commented. So I thought we would just kind of read the comments and go through it, and I'll add some additional context. I might also make some notes because I see things that I would like to change. At the point of this recording, Impact is still in like release candidate mode, which is basically prepping it for the official release. But yeah, hopefully this gives you some nice insight. So let's get going. Now, first of all, there is this symbol dispose, which is a polyfill. This symbol, as Safari currently does not have it. And this is related to explicit resource management, which is a new JavaScript feature that allows us to use the using keyword related to consuming a store to implicitly observe any signals you consume from that store. And Safari doesn't have symbol.dispose, and we'll see later how we actually use that. But yeah, so we need to do that. And then we have signal debug hooks, which is an object that is used by the Impact React debugger to access internals. And I found this to be a good pattern building libraries where you want a debugger. So basically you just export an object where you just create all the hooks. Like what does the debugger want from the internals? And you just create these hooks that provides that data or that information. And then when you import the debugger, you just need to import the package. And then the debugger itself will register to these hooks. And then through the code, it just checks if the hook is there, and then it will call it. So that's been a very efficient way I found to do that kind of thing. We need to know if we're in production, if we're using the debugger. And then we have something called the current snapshot. And this global counter makes sure that every signal update is unique and can be tracked by React. So the thing about observables and observing is that whenever you change a signal, and that signal is observed in an effect or a derived, it will synchronously observe that and react to it and resubscribe to its observer context, right? But this doesn't happen synchronously in React. So in React, you have this observer context and it's notified about the change to a signal that's registered on that observer context. And then React uses the useSync external store, which will go in and try to reconcile. And between the reconciliation and adding the subscription again, it's async. And what useSync external store does is that it checks something called a snapshot. And that snapshot basically represents, has anything changed? As long as the snapshot is the same, the store that it syncs with represents the same state. And we'll see later how this is actually applied, but that's the reason we have it. And then we have resolving store containers. A store container is like an injection container. It is responsible for resolving stores, which I talked about in the abstract part. As stores can resolve other stores, we keep track of the currently resolving stores. A null store is a global store. And here I already have a to-do that we should probably use a symbol instead of null. It's weird to use null as a reference for something that exists. But you're tired and you just want to make it work. Then we have store providers. By default, Impact resolves to a global store. If a store provider is created for a store, we keep track of it. That way we can throw an error if the provider has not been mounted when trying to consume the related store. So basically when you call create store provider, we'll register here that this store requires a store provider. So when a component tries to resolve that store and it doesn't find its provider, we'll actually throw an error because we know that it needs to be provided, as opposed to letting it through and register globally. And then we have our global stores. If we resolve the global store, we keep the resolved stores here. An active component observer context. We only want a single observer context for a component, but you can use multiple useStore. Like you can consume multiple stores in a component, but the observer context is tied to the component, even though it's the useStore hook that creates it. So we keep track of the currently active observer context to only create one for each component, regardless of like how many stores it consumes. Then we have a helper called getResolvingStoreContainer. Identify if we have a resolving store. This allows the global cleanup function to register cleanups to the currently resolving store, right? You import the cleanup function. It's a global function. You just use it in a store, and it needs to know where should it register its callback, like what store is currently being resolved. And this is very much like tied to how observation also works. Like you're just referencing something outside of the effect or the derived or whatever. And it just needs to know what's the current observer context. Well, here it's what's the current resolving store. Then we have is resolving store from component. We need to know if we are resolving a store with an active observer context for a component. If so, we do not want to track signal access in the store itself. So you can imagine you're mounting or you're rendering the component using a useStore, which actually resolves a store, and it needs to be instantiated. And this happens synchronously. So as part of reconciling or running the component function body, it will also run the store function. And if you would happen to actually access a signal during that, it will, by default, that will be registered to the component observer context. But the component observer context doesn't care about that. It only cares about the actual signals accessed in the component function. So that's what this does. It helps identify that scenario. And then we have the type for the store. And then we keep track of the resolved state of a store. Is it resolved? Value here is, you know what? We're gonna do change value to store. And we have this constructor to store constructor. I want to be a bit more explicit here. Anyway, so a store can be resolved. Then we have the instance of the store, and we have a reference to the store. And if it's not resolved, we have the constructor, which is basically the store function itself being called with the props coming into the provider. That is the constructor. And then we have the actual store container. A store container is created by the store provider in React. When using the uStore hook, it first finds the context providing the store container and then resolves the store. So the store container handles some error things, and there's some special stuff happening in React where we need to keep track of an error. I won't go into that. And then we have the actual state of the store container, or the store state. And then we have the disposers, which are like any cleanup callbacks that we need to keep track of. When constructing the provider for the store, we only keep a reference to the store and any parent store container. So this is how it's able to keep resolving stores up the component tree, is because that this store container actually has a reference to any parent store container, which is coming from the React context. We'll see that later. We start out with an initial state. Here we have a register cleanup. When resolving the store, we use a global cleanup function, which accesses, it's a typo, accesses the currently resolving store and registers the cleanup function. And then we have the big magic resolver. Well, it's not magic, but it's actually quite straightforward. So if we have an error and it tries to resolve, we're going to throw that resolvement error. If we're trying to resolve the store this container is responsible for, and it has already been resolved, we can just return it. And if we are trying to resolve the store this container is responsible for, and it has not been resolved, we resolve it. And the way we resolve it is that we try to resolve it. And we first push to resolving store containers that we're resolving this store now. We're changing the state by basically calling this constructor, which is the store function itself with the props. And we keep a reference to the actual store. And when this happens synchronously, so immediately we'll pop it off and we'll return the store. And remember that calling this we might call a store that's using uStore for another store, right? So it kind of builds up the resolvement. So if we have an error, we'll throw the error, could not initialize the store. So if the store is not matching this store container, and we have a parent, we start resolving the store at the parent instead. So you might have a store that's trying to resolve a store that's not the immediate provided store. So it just goes up the React context, basically, and tries to resolve the store. And then if we could not resolve the store through the context, but the store has a register store provider, we throw an error. And at this point, we default to creating a global store, if not already created. So if we don't have it, again, we push null, which represents a global store. We resolve it by just calling the store, because it doesn't have any props or anything. And then we keep a reference to it, and then we return it. And then we have a cleanup for the store container itself. So this happens related to unmounting the provider. So when the provider unmounts, we do a cleanup, which basically runs any cleanup callback that you provided to the store. And then we have the actual store container provider. So there's like two parts to the provider. You have the actual store provider that kind of you use and see. But we also have like an underlying store container provider. So this is a class component, and it has, and this is how, if you remember class components, this is how you consume a context. So this is trying to consume a store container context from above, right? It's kind of like use context in a function component that we're doing here, so that we can find a parent store container. And then we have to track the mounted state. So we need to track the mounted state, as strict mode will call component did mount and component will unmount twice, meaning we'll clean up too early. This is a safeguard against side effects in React to allow this component to be part of suspended rendering. Suspended rendering means it might render it, but never commit, meaning no call to component did mount or component will unmount. We have to resolve stores during reconciliation and cannot rely on component did mount. That means this component does not support suspended rendering. This is documented, and we throw an error if this happens. I think I'm mixing concepts a little bit here. One thing is like only running the rendering phase. Another thing is actually calling using strict mode, where it's called twice. To do rewrite this to better separate dispose render phase and strict mode. Yeah, I'll give a better explanation there. But yeah, so we need to handle strict mode. And the point is that here we have a very controlled way of doing things. It's not like just some component where you try to create some side effect. We know exactly what's happening here, and we control the concurrent mode, like you're not running this in a potentially disposed render phase, and so on. So this is something that's fine to do when it's in such a controlled way. And let's see here. Let's just continue reading the code and we'll get to this stuff. So we'll create a store container that receives the store and the actual props pass to the provider. And these props, they are now actually signals at this point. And then we pass in this.context, which is potentially a parent store container. So when we mount, we say true. When we unmount, we say false. And then we just do a micro task to figure out if we actually did unmount. And if we did unmount, we run the cleanup. So that's why we have this flag to track that. And it's very, yeah, this stuff is kind of frustrating. But I understand that React isn't like state management. It shouldn't have side effects and all of this stuff. So it does make sense, but at some point you have to be able to instantiate something during the instantiation of the component itself, like before it starts like running the function body, or you want to instantiate something and use it during the rendering of the component. But that's not like supported really in React unless you add some additional checks. But it's nice to not have to think about that from a developer experience perspective. So then we have the render, which creates the the provider and passes the container, store container, as a value on that context. And then as part of the child, we create a suspense, or as part of the children, we create a suspense, and this suspense is there only to throw an error. So you can imagine if you mount a store or you provide a store and you use the use hook in a nested component without putting a suspense boundary between the store provider and the component that uses the use hook, it will hit this suspense. And that will throw an error and say the store provider does not support suspense. Please add a suspense boundary between the store provider and the component using suspense. And that is what I talked about in the abstract part. It's that we don't know when React chooses to discard a component tree that's only gone through its render phase. Yes. And then let's move on. Here we have our global cleanup function that takes a cleaner callback. We allow running this cleanup function globally. It uses the currently resolving container to register the cleanup function. And the way it does this is that and here we can kind of see the weirdness of using null. We have to explicitly check and define. So if we're not resolving a store container, we throw an error because it's an invalid use of the cleanup function. And if it's a global store, we just ignore it. Explain why. I can't remember. There is a. Give me a few seconds if I can remember why we don't throw an error here. Yeah, I cannot remember. There's a reason why we don't throw an error. You might say that, well, it's invalid to use cleanup in a global store, so we should throw an error. But there's a reason, and I can't remember it. So let's just make a note of it. But if everything's good, we register the cleanup to the currently resolving store container. And then we have useStore. I need water for this one. useStore can be used in both components and stores. When resolving from a component, it will create an observer context and resolve the store. If resolving from a store, it will only resolve the store. That makes sense, right? So let's see the implementation. First, we go and see if we have a currently resolving store container. And if we are not currently resolving a store, we assume that we are resolving from a component, as you can really only initiate resolving stores from components. And so if we are trying to resolve from a component, we try to find a store container on the context first to resolve a store from it. And then if we can actually find a store container on the context, we try to resolve our store from that one. And as I said, we might not be trying to resolve like the store that is bound to the store container that we find to be the nearest parent. It might need to like jump up the component tree, like the context, to find the actual store that we're trying to resolve. That's kind of the injection store. That's why it's a container. It's kind of its own like injection mechanism. I already talked about this. But again, we go here and we actually check if we didn't find a store container, but we expect it to have a store provider. We're going to throw an error. So we do this also we did this already in the store container, right? But we might be resolving a global store directly from a component. So we need to also check it here. And then if we do not find a store container, we resolve a global store. And if we don't have a result store, we go and create it, doing the same thing. And then we go and check if we already have an active component observer context. As I mentioned, it might consume multiple stores. So we check if we already have an active component observer context. And if we do, we still register the symbol dispose method. So that's the mechanism of actually observing, is that when you do useStore, we'll add a symbol.dispose method to the store temporarily, which will kind of end the tracking of the current observer context. We'll see it in the next lines here. But if we already have an observer context for this component, we'll still add it, and then we just remove it when it's done, because you're still using the using keyword, right? So it needs to have this method or it will throw an error. So at this point, we are consuming the first store in the component, and we need to create an observer context. So we use this use observer hook, we can look at that later, that basically sets up our observer context. And then we have some helpers to make sure that you're using it correctly so that you don't forget to use the using keyword. And that's what's happening here. Has used explicit resource management. And if we're using the debugger or we're not in production, we're going to go and give you a good stack trace. And then we're going to do a micro task to figure out if you actually did this correctly and throw an error if you didn't. And then, as I mentioned, we have this result store. We add the symbol dispose method to it, where we set that. And this method, this symbol.dispose, this is what explicit resource management does. So the store now represents like a resource because it has this symbol.dispose method. So in combination with the using keyword and having this symbol.dispose, when the component function is done running, regardless of like it throwing an error or whatever, this symbol.dispose method will be called last, like at the very, like after it returns, after everything. And that's exactly where we want to say that we don't have an active component observer context anymore. We don't want to track any more signals. And we go and delete the symbol dispose again. And we pop the current observer context off the stack, because having observer contexts, they might, like you might start in a component and then maybe we'll add an observer context because you're consuming a derived, for example, and so on. So these kind of stack on top of each other, and we pop them off the stack until it's empty. And then we return the result store. And then at this point, we're not in a component. So this was the component section. And at this point, we're not in a component. We are in a store. And we just resolve it as normal, where we again have this little helper that if you're using the using keyword inside the store, you don't have to do that. Like it won't break, but you don't have to do that. Okay, and then we have the create store provider. So this function creates the actual store provider component, which is responsible for providing handling for handling the children and only pass relevant props and the store. Okay, let's to do rewrite and include signals. Like I haven't documented here that it's responsible for making the props into signals. So what we see here is that when we call create store provider, we add the store to store providers so that we can throw an error if we don't use the provider. And then we define the provider itself, which takes in some props and children, and we make a copy of the props where we extract the children and then delete the children from these extended props. Not sure why I call it extended props. Because we don't want to pass the children into the store, right? It doesn't make any sense. Then we create this ref for the signal version of that prop. So if we don't have any signals created, we just go through the props and we create a signal for each prop. And then when we run useEffect, we'll go through the props again and we'll find the related signal and update the signal. And since signals has the same concept of like immutability, the signal will check if the value actually changed. So for example, in the first run here, it will create the signal, but it will also try to update all of the signals again. But they won't actually update because it's the same value, just like useState. If you pass it or try to set the same value, nothing happens. But if the value has changed, like React has reconciled, the prop has actually changed its value, the signal version of that prop inside the store will notify, and any observers of that signal will reconcile. And then we create actual store container provider with the prop signals, and we're passing the store, and we have the children here. Cool. And then we get to the observation part of Impact. So the observer context is responsible for keeping track of signals accessed in a component, derived, or effect. It does this by being set as a currently active observer context in the stack. Any signal setting/getting will register to this active observer context. The component derived effect then subscribes to the context, which will add the context to every signal tracked. When context is notified about the change, it will remove itself from current signals and notify any subscribers of the context. It is expected that it's really only a single subscriber at any point, but it's expected that the subscriber of the context will initiate tracking again. So it will register, because it's dynamic, right? So you might have other signals based on a signal being notified in a context, or a context being notified by a signal. For example, a derived, there might be other signals tracked because of that. So it needs to re-add the signals for every time derived runs. Anyways, we initiate tracking again. The subscription to the context can be disposed, which will also remove the context from any tracked signals. This makes sure that component/store, a component unmount and store disposal will also remove the context from any signals, making it primed for garbage collection. So we rely on garbage collection for the signals. So that means that an observer context, an observer context can't rely on signals. Because if it does that, like signals will most signals will live through the lifetime of the application itself. They will always be there. So we can't put those signal references into a context. We have to put the context references into signals, so that when a component is not being referenced anymore by React, like all the objects and all the memory related to a component is not referenced anymore, we have to make sure that the observer context is also not being referenced by any signals, right? So that is why we control this unsubscribe, where we remove the context from the signals that we prime it for garbage collection. Yes, so here we have the stack. We keep a global reference to the currently active observer context. A component might first create one, then resolving a store with a derived, which adds another, which might consume a derived from another store, which adds another, etc. And then we can go and grab the current observer context. And then we have the set getters and setters and subscribers. We need to keep track of what signals are being set and get. The reason is that in an effect, you cannot both get and set a signal, as observation would trigger the effect again, creating an infinite loop. So in an effect, we prevent notifying updates when a signal has both a getter and a setter. This is also used for debugging, like accessing these things, so that we can actually see what signals are being used by the observer context. But yeah, in an effect, if you're trying to set a signal in an effect, but then you're also accessing, unwrapping the value of the same signal, it means you're observing the change to the signal and you're setting the signal. So that creates the infinite loop. But we're able to know about this and just prevent it from happening. Like if you're setting the value of a signal, if you happen to also get the value of a signal, it just won't trigger observation. And then we have the snapshot. So components are using useSync external store, which expects a snapshot to indicate a change to the store. By the way, I haven't put the code in order, so you'll have to excuse us like jumping between concepts here. I'll see if I can find a nice order of functionality, kind of group it more together. But yeah. Anyways, components are using useSync external store, which expects a snapshot to indicate a change to the store. We use a simple number for this to trigger reconciliation of a component. We start out with the current, as it reflects the current state of all signals. So as I said, every time a signal changes, it bumps kind of this snapshot version. And then when we create an observer context, we say that this is the current snapshot. So that whenever useSync external store runs, it tries to get the snapshot, it will just get the same value, right? By default. But as soon as one of the signals it's tracking notifies observer context, it will pass in the new bumped snapshot value and update the snapshot value of the observer context so that when useSync external store tries to reconcile, it's able to now check the snapshot, because notifying useSync external store to update will not update the component. It will only trigger a check for the snapshot, and that will determine if it will reconcile again. Okay, so here we register the getter. If we already have it as a setter, we don't add it. When we register a setter, we see if it's registered as a getter. We remove it from the getter and set it as a setter instead. This is the infinite loop I was talking about. And then we have subscribe. So when adding a subscriber, we ensure that the relevant signals are notifying this observer context of updates. That means when nothing is subscribing to this observer context, the instance is free to be garbage collected. React asynchronously subscribes and unsubscribes. But using, well, I should put reconciliation. It's related to reconciliation here as well. Yeah, but I think that's fine. So it's reconciles and then asynchronously subscribes. But useSync external store has a mechanism that ensures the validity of the subscription using snapshots. So when it reconciles, it checks the snapshot, it reconciles, it's going to subscribe, but it checks the snapshot first. Has the snapshot now changed since I reconciled? If it's changed, it will reconcile again. Let's see. So basically, that's what we're doing here. We're adding the subscriber. If, again, it's really only a single subscriber, but but we handle it as potentially multiple subscribers. Could maybe change this. Yeah, we should do that. Move back to single subscriber. Just better explains it. So here, if the subscriber size is 1, we go through the getters and we actually add this context to those signals. As I said, we can't do the opposite because we don't want, we have to, like the signals are long-lived and the context is short-lived in terms of components. And we want to have a simple mechanism to ensure that this observer context is garbage collected, and it will be because there's nothing referencing the context other than the thing that created it. So here, when we unsubscribe, we delete the subscriber. And if the subscriber size is 0, we go through the getters and we remove the context. Okay, so then we have notify. So notify is called by signals because the signals, they have a list of contexts that's kind of detected that they've been accessed during the context execution or the scope of the context. So when a signal changes, it goes through its context and notify with the new snapshot. So we say that we update the snapshot and then we clear the tracking information of the observer context when we notify, as it should result in a new tracking. So we'll just go in, we'll remove the context from all the signals, we clear the getters, we clear the setters, and then we go and we notify the subscribers that we have an update, where they will exit, if it's an effect, it will run the effect again. If it's a derived, it will actually mark itself as dirty and then lazily run again. And if it's a component, it will update using external store, and it will evaluate based on the snapshot that it should reconcile again and then resubscribe. The thing though, and this is a thing that's hurt me a couple of times, is that when subscriptions can synchronously be removed and added. So we need to make sure we only iterate the current subscribers, or the set will keep iterating forever. This is a funny infinite loop. It's like if we were only to do this subscribers dot for each, if notifying that subscriber resulted in adding the subscriber again to this set, because it synchronously unsubscribes and subscribes, it will just keep running the set. It's very interesting. Anyways, and then we have the signal notifier, and the signal notifier can be thought of as, well, being a notifier for the signal. This is instantiated by a signal to keep track of what observer contexts are interested in the signal and notifies them when the signal changes. So here we can see the signal notifier has a set of contexts. It has a snapshot. A signal holds a global snapshot value, which changes whenever the signal changes. This snapshot is passed and stored on the observer context to make sure React understands that a change has happened. So we just add a snapshot whenever we create a signal notifier, because a new signal, it's not only a new value to signal that changes the snapshot, it's also a new signal. I'm not sure if that's needed, but that's how it is. And here we have what we were calling from the context, the ability to add context and remove context. And then we have notify, which is being called by the actual signal. So when a signal calls notify to notify the context, it will bump the current snapshot. I wonder, yeah, it should be like this. Oh, we should evaluate this here because I changed this. I called it next snapshot. I think actually this one should be on the other side. It's not a huge deal, but I think we should have the on the other side. So we'll add to the current snapshot after we set this. I'm going to check that. And a context can be synchronously added back to this signal relative to firing. So we have the same thing. So to avoid creating a loop, we're going to extract the current context and then notify them. Cool. And then we have the actual signal here, the typing for it, which you can see handles the observable promise inference. And then since the signal supports promises as a first-class concept, we say that if a signal has a promise, we want to abort the current resolving promise if we're changing it to a new one. So we use an abort controller for that, so that whenever you try to set a new promise, we'll abort the current promise, right? And then the value is If it's a promise, we're going to create an observable promise. If it's not, we're just going to use the value. And then we create our signal notifier, and this create observable promise is just responsible for updating the promise in the signal. So we'll abort the current abort controller and then create a new one. And then we'll create a pending promise, which is just enhancing with the status properties and stuff, where when that promise resolves, we return if it's been aborted, or we'll create a fulfilled promise and notify our signal that it's been updated, or when there's an error, it's the same. And then we return the function that represents the actual thing that you use as a developer, where we check that if we don't have any arguments, it means you're just calling the function, which means we should unwrap the value. And if we have an observer context and it's not resolving a store from a component, if you remember, if it's in a component, we only want to track the signal's access in the component, not because it happened to resolve and instantiate the store. We register the getter, and if we have a debug hook, we run that, and then we just return the value. But if we're trying to set something here, we first check if it's a function, and then we call that function with the current value to give us a new value. If the new value is an instance of a promise, we're going to create an observable promise from that. And we do nothing if the values are the same. And then we update the actual value. We register a getter if we have an observer context. We have the debugger thingy here. And then we check again if the new value is an instance of a promise, because a promise could be an already resolved promise, in which case we do not want to notify as it is already done in create observable promise. So we run our own microtask to check if the promise is still pending, where we do not want to notify. Where we do want to notify, sorry. So the point is with, like, when you think about your signal as an async value, and you kind of just want to set a new value, that needs to be set as a promise. But what would happen here is we just trigger the signal immediately, is that it will trigger twice, right? For setting the promise, and then again immediately, well, not synchronously immediately, but micro task immediately, the resolved value. So we can very simply figure that out by waiting a microtask, and only if it's still pending, we're going to notify. But if it's not a promise, we'll of course notify immediately when the signal is updated. And this is also a thing, like React has evolved a lot, and who should be responsible for batching changes? The way I think about it in Impact is that React already has a mechanism in place. Like if you create a use state in React and you kind of call it many times, like synchronously, it will only run once. So React has its own its own internal batching of state changes, which also happens with using external store. So the perspective of Impact is that it's React's responsibility to batch changes. It's not the responsibility of this library. So that means that if you're like changing a bunch of signals, it will notify the context multiple times. That context might tell React to render multiple times, but because it's synchronously happening, React is doing the batching for that. But it is possible to do batching here as well, but it's not implemented because React handles it. And then we have the promise creators. We have the polyfilled use hook, which is basically just throwing a promise. And then we have the derived. Oh, did I pull the latest? This is, I believe this is actually fixed. Let's see. git pull. Oh, this should be fixed. Wait, am I on which branch? Am I on the branch? Oh, it's behind. Oh, can't I pull? Oh, git stash. Sorry, git stash, git pull, git stash pop or something. Yeah. There we go. Sorry. So in the derived, we get resolving store container. I had a bug here because using null. If it's undefined, we're using derived in a context that's not valid. The thing about a derived is that it's lazy. So we have this flag called dirty. We keep track of it being dirty because we only compute the result of derived when accessing it and it being dirty. It is lazy. And then we have our signal notifier. We create a context, observer context for it. And whenever the store unmounts, we clean up the derived. And again, we do not want to track access to this derived if we're resolving store from a component, blah, blah, blah. And then we check if it's dirty, which is its default state. We push the observer context on the stack. We run the callback. We pop the observer context off the stack. We subscribe on the context to put this observer context on these signals. And we set is dirty to false. But when the subscription, like the observer context notifies that there's an update here, we go, when notified about an update, we immediately unsubscribe as we do not care about any further updates. When the derived is accessed again, it is dirty and a new subscription is set up. So the only thing that happens is that we set it to dirty and we notify. So if any contexts are interested in this signal representing the derived, they will go and grab the value again. But if there aren't any, it will just stay dirty until something accesses the derived. And it's kind of the same for effect. We run the effect, we dispose of any subscription, we push the context on the stack, we call the effect, we pop it off the stack, and we subscribe to it. And when we do that, we just run the effect again. And that's basically it. And then we have, I can't believe we actually got through this. The hook that syncs React with observer context, use observer. So this is what actually happens, like in terms of the observer context in a component. We keep a reference to an observer context, and we push that on the stack as the component body executes. And oh, this is old stuff. Yeah, sorry, that was an old comment. And then we have use sync external. So we subscribe to the context. This only notifies about the change. We then grab the current snapshot, which is the global number for any changes to any signal, ensuring we'll always get a new snapshot whenever a related signal changes. Yeah, I guess that's fine. Server-side, Impact isn't really built for running server-side. You can, but I don't think it makes sense. Like, it's more designed for these, as I mentioned in the presentation, complex single-page applications that doesn't really do server-side rendering, but it's more of like an application running in the browser. Cool. Yeah, so that's all. Maybe some approaches here could be better. Maybe there are some, it could be organized better. Maybe there are some bugs here. Who knows? But at least it's something that's grokkable, right? So hopefully this helped you kind of get an understanding of the code base and helps you contribute to it, and maybe it inspired you to do something on your own, or it was just educational maybe. But yeah, thanks for watching, and